last thing to discuss with relation to equilibrium, and I've been working on updating the equilibrium presentation that I know we haven't actually used. So I'll print this off for you once it's all done, and you can have that for notes as well. Okay, so concentration time graphs is the last thing that we need to talk about. So yesterday we were talking about ice tables, or ice cube tables, if you want to think of it that way. We're changing and manipulating things. Now we're going to look at concentration time graphs, and this links with the number 3 prac that we did last Thursday, right? Because there was a lot of graphing involved in that. So remember, we're looking at homogeneous equilibria, right? Homo meaning the same, right? Genus referring to like the state of, so the same state, where state of reactants and products are the same. So either they're all going to be aqueous or all going to be gaseous. Concentration of liquid and solid states do not change. So, but we don't really look at liquids and solids. Yeah. Concentration time graphs, right? So if we consider a gaseous species and we're adding a substance, right? So going back to this example of, let's grab my, right, this Haber process that we've talked about at length, ad nauseum probably, right, because it's quite a well-known equilibrium system. So if we're going to add reactants, remember the concentration of reactant species increases. The effect is that QC becomes less than KC, right, because reactants is on the bottom, right, meaning that the value of QC goes down, so we must shift forward in order to bring back to equilibrium. Remember that there's this key word in the wording of Le Chatelier's principle talking about the partial adjustment to oppose the change. Yeah? So a change happens to the system partially adjusts to bring the system back to equilibrium. I highlight that particularly for concentration time graphs. So let's take this example. I've got my Haber process going on. I'm going to say that the reaction is at equilibrium for a certain amount of time. Then at some arbitrary time, let's call it T1, I'm going to insert more nitrogen gas. Yeah? Inject it in. Yeah. Yes. So we're going to do it rapidly. So we're going to call it an instantaneous change. I've taken a bunch of gas and I'm injecting it straight into the system. If you inject it slowly, yeah, you'd probably see a graph like this. Yeah? But if we're talking about adding or subtracting a substance from the system, it's going to be an instantaneous change, rapid jump up, right? So rapid jump up, concentration of this increases, drives the reaction forward. What does that do? It starts to decrease N2 and decrease H2. Note this thing about partial change. We notice that when it returns to equilibrium, which is this point here where the lines flatten out again, notice how it doesn't go back to the initial concentration. So the concentration of N2 still remains slightly higher once equilibrium is re-established. Note also the difference in height, right? Even though the concentration is not to scale, the arbitrary differences is stoichiometrically proportionate. We've talked about stoichiometry. So for every 1 loss of nitrogen, we would lose 3 lots of hydrogen. Does that make sense? Right? So if we call that distance to there 1 unit, then the distance from here to there should be 3 units in size. Yeah? And the addition of ammonia will be twice the distance lost of nitrogen. You with me? Cool. Let's look at another example. Pressure, right? Remember, pressure by a change in volume changes the equilibrium system. Pressure by the addition of inert gas, what happens? Nothing, yeah? Partial pressures, concentrations of species all stay the same. No change to QC or KC, no shift in the reaction. Well, it doesn't have to be argon, but any non-reactive gas. So in this example, if I added nitrogen gas, nothing would happen because nitrogen is not involved in this reaction. If I add nitrogen gas in this reaction, something happens. If I add it in this reaction, nothing happens. That makes sense? So it's a non-reactive gas. It doesn't have to necessarily be a noble gas, but just a gas which is non-reactant in the equilibrium system. Cool? So pressure change by a change in volume, right? If I decrease the volume, I increase the concentration of all chemical species, yeah? We've got that here. Oh, I should, yeah. So concentration, this should say increase. That's terrible. Decrease in volume results in an increase in the concentration of chemical species, yeah? And we see that as we jump up the concentration of all our chemical species. Now, if this was to scale, right, stoichiometrically speaking, if oxygen goes up by 1 unit, all right, if we halve the volume, we would double the concentration of oxygen. We would more than double the concentrations of all the chemical species by, yeah? So if this was at 2, this would jump up to 4. If this was at 3, it would jump up to 6. If this was at 1, it would jump up to 2, right? So the relative changes will be different. So increase of pressure by a decrease in volume increases concentrations of all species. Reactants have a net greater effect, so it drives the reaction forward to fewer particles, yeah? So we can see that SO2 and O2 start to decline, or O2 here. Oh, why is that increasing? No, this is wrong, I realize. SO2 should also decrease. So this graph is wrong from the text, so I'll fix up the graph. So we should have it whereby this should decrease twice the value of the decrease of oxygen. So this should go down and this goes up. I'll fix that graph, okay? I only just picked up that mistake. Okay, now this was the reaction we looked at last week. Changing the volume of N2O4 and NO2. NO2 is brown. N2O4 is sort of a yellowy, colorless, right? Before compression, we've got that mixture of yellow and brown. Compress, immediate change, we see it go really dark. And then it lightens. But notice, I don't know if you can tell on here, well, you should be able to tell. Notice how this is darker than that. Yeah? So the shift is towards the brown, towards the yellow, right? But the initial change is dark, and the overall change is that we have a shift towards the backwards reaction, but still appears darker than before, right? So think not just in terms of shift, think in terms of observation as well, yeah? So we can see that. Compress, instantaneous change, both concentrations go up, right? Both double. N2O4 starts to increase, NO2 starts to decrease, partial change, so it won't decrease back to this line here, yeah? You're not expected at year 12 to determine what these specific concentrations are, right? But you would be expected to know that it should not return back to this point. And you should be expected to know that this would double if I had a halving of the volume. Yeah?
So when you increase the pressure, always the backwards reaction?
No.
How does it say?
In this equilibrium system, it would be backwards. In any other system, decrease in volume shifts in the direction of fewer particles. So in this reaction, it's forwards. In this reaction, it's backwards. Yeah? Because the number of mole of this effectively is a greater effect compared to the net change in this, which is why when the number of particles of reactants and products are the same, we don't get a shift. So if this was, I don't know, for argument's sake, 2NO, if this was a number 2 in front going to a number 2, right? Then we would just see that.
Yeah.
And we wouldn't see a shift.
Because it's trying to make less molecules in the volume.
Yeah, so if they're the same on both sides of the equation, there's no shift in the reaction. Yeah? Okay. An increase in volume, so like a dilution or increasing the volume of the container. So let's look at an addition of water example. Concentration of all species decreases. Fix that up. The shift shifts towards the side of more particles. So in this example, this is the one we looked at. We looked at a dilution, right? We've got 2 particles on this side, 1 particle on this side. We're going to have a net backwards reaction. More particles on this side with a volume increase. Right, graphically, instantaneous change, concentration of all species dramatically decreases, right? This continues to decrease. These increase, right? Proportionally all the same because it's 1 to 1 to 1. So the difference between here and here, here to here and here to here will all be the same. Partial adjustment, so reminding you of that again, that we don't go back to that initial equilibrium level. Yeah? Cool. Okay. Temperature changes. Remember I was talking about how Kc is temperature dependent. So if we've got a chemical species that's already at equilibrium, this is how we tell that there is a temperature change. Notice how there's no instantaneous change in the concentrations. Yeah? So I said that. No immediate change in the concentration of chemical species. But there is a shift, and we can see the shift in which both of these species change. Yeah? No dramatic increase or decrease. So if all concentrations change up or down, we're changing the volume. If only one changes up or down, we're either removing it or adding it to the system. Yeah, so as this is written, notice I've written it in the opposing direction as this. Yep, just to confuse you, right? So in this, we can see that N2O4 is decreasing. So we've got a shift towards the backwards reaction with an, with an increase in temperature. If I've got a shift in the backwards reaction, that tells me the backwards reaction is endothermic. So therefore, the forward reaction is exothermic. Yeah? So if we have an increase in Kc with an increase in temperature, it's endothermic. If we have, so the same effect, if we have decrease in Kc, we have a decrease in temperature, endothermic, increase, endothermic. If we have the opposing, so increase in temperature with a decrease in yield of product, exothermic reaction. And as I've said there, the increase in the concentration of NO2 highlights that the backwards reaction is endothermic, and thus the forward reaction as written must be exothermic. Right, last thing to talk about that's not going to be on the SAC, and that relates to competing equilibria. We only look at one competing equilibrium reaction in Year 12. And that's carbon monoxide poisoning. So we want to be able to apply Le Chatelier's principle for this. Remembering that complete combustion is what? Right, oxygen's in excess. Incomplete combustion? Oxygen is limiting, resulting in carbon monoxide as the byproduct. Rather than carbon dioxide, the amount of energy released is lower, less efficient. Hemoglobin, we don't really need to know what it is, but essentially it's a protein that's in red blood cells. Right? It's the oxygen carrying molecule. Each hemoglobin is made, it's a what's called a quaternary structured protein. Who does biology? There you go. You know what quaternary structure is? What's the primary structure?
Single polypeptide chain.
Right? So the sequence of amino acids, what's secondary structure?
Polypeptide chain bonding to itself.
Right? So you got your alpha helices or your beta pleated sheets. Yeah, what's your tertiary structure?
Bonding to each other.
Right? Bonding between side groups. You'll need to know this for Unit 4.
Wait,
And what's the quaternary structure?
Is multiple.
Multiple